Good morning and welcome to an insightful exploration of the world of queuing theory. In this video, we will delve into the world of queuing theory, emphasizing its vital role in analyzing waiting lines and optimizing service processes. We will discuss its practical application in various fields such as telecommunication, customer service, and transportation, highlighting how it facilitates the efficient management of resources and enhance operational efficiency. So let's start with the basic question, what is a queue? A queue is a line or sequence of people, vehicles, or any other thing awaiting their turn to be attended or to proceed. I am pretty sure that at least once in a day we have been in a queue. So some good example of queue include waiting in line, lining up to pay in the supermarket, and waiting in the line to check your account balance at ATM. However, queue are not always present for people. They can also be for airplanes waiting for their turn to take off at airports. Jobs or products can wait in an assembly line, and perhaps the most annoying, traffic. So what is a queuing theory? Queuing theory determines the measure of performance of waiting line, which can be used to design services. It is not an optimization technique because waiting cannot be completely eliminated without incurring excessive expenses. The goal of a queuing theory is to reduce its adverse impact to tolerable levels. Therefore, queuing theory does not provide solution but rather measurement or analysis of queues or different lines. There are six different characteristics of a queue that we will go through one by one. The input or arrival distribution, the output or departure service distribution, service channels, service discipline, the maximum number of customers allowed in the system, and the calling source. So let's explore each of these characteristics with example. For instance, consider the scenario of paying in a grocery store. You have a server and different customer with grocery store acting as a source of line. The service time is the amount of time that the cashier or the point of the sale system take place to attend your needs. It usually follow a negative exponential distribution. The inter-arrival time between customer follows the Poisson distribution. So let's consider a scenario with three server and one line. The three server represent the service facility and the one line is the queue or the waiting line. The people in the queue are the arriving customer while those who have just finished being served are the departing customer. The queue plus the waiting line along with the service facility is called the system or the entire system queue. Zooming in on a single line, the queue size is the number of people that one queue can accommodate, either finite or infinite. The customer in the queue can exhibit different disciplines such as first come first serve, last come last serve, service in random order, or priority. Three common reactions for each customer in the queue can be observed: joking, barking, or reneging. Let's consider example of two servers and two lines. Joking refers to the act of customer switching from one queue to another, usually because they perceive the other queue to be faster or more efficient. Joking often occurs when there are multiple lines or queue and customers are allowed to change lines. It can lead to inefficiencies in the overall system as the switching of customer can disturb the equilibrium of the queue. Barking. Barking occurs when a customer decides not to join a queue or a line because the queue length is too long or the wait length is perceived as being too excessive. This behavior is often influenced by the customer's perception of waiting time and the importance of the service they are seeking. Barking can be a significant issue for businesses as it directly impacts potential revenues and customer satisfaction. Reneging. Reneging happens when a customer joins the queue but then decides to leave before being served. This behavior is typically triggered by long waiting lines or delays that exceed the customer patience threshold. Reneging can be problematic for service provider as it results in both lost revenue and potentially dissatisfied customer. Putting these two characteristics into mathematical form, we have what is called the Kendall notation. The Kendall notation consists of six different characteristics as mentioned earlier, each represented by specific symbol. So additionally, there are various symbols used in queuing theory such as lambda, mu, rho, n number of servers in the system, probability of n, c, total number of customers, ws, wq, ls, lq, average time in the system, average wait time in the queue, average total customer in the system, average customer waiting time in the queue. So let's talk about Kendall notation, which can be broken down into six parts: A, B, C, and D, E, F. A is known as input or arrival distribution, which can take many distribution like Markovian or deterministic and many more. The second part is B, which is output or departure distribution. It can also take many distribution like exponential or deterministic and many more. Next is C, which is a service channel. Further, service discipline, which is known as D, can also be broken down into four parts: first come, first served, last come, first served, service in random order, and general service discipline. Next part is E, which is maximum number of customer allowed in the system. Next part is F, calling source, which can also be broken down into two parts: finite or infinite. So to illustrate, let's consider an example. A gas station has one pump that can serve 6 customers per hour. Cars arrive at the station at the rate of 10 per hour, following an exponentially distributed pattern. Using the MM1 notation, we can calculate different patterns like the mean arrival rate, the mean service rate, utilization factor, as well as the expected waiting time per customer in the system and in the queue, and the expected number of customers in the system and in the queue. So we can get our lambda and mu, which is our mean arrival rate and mean service rate. So our lambda is 10 car per hour, so which can be converted or written as 1 car per 6 minutes. So our lambda is 6 minute and mu can be written as 6 car per 60 minute into 1 car per 10 minute, and our mu is 10 minute. Using various queuing model formulas, we can calculate expected waiting time per customer in the system and expected waiting time per customer in the queue and expected number of customer in the system and in the queue, which are 0.25 hours, 0.15 hours, 2 cars and 1 car respectively. At last, we will see 5 different models. First is MM1 GD infinity infinity. In this, the queuing model is in which the arrival is Markovian and the departure distribution is also Markovian, and the number of customers is 1 and the service discipline is general. Size of the queue is finite, calling source is also infinite. The next model is MM1 GD and infinity. This is a queuing model in which the arrival is Markovian and departure distribution is also Markovian. Number of server is 1 and the number service discipline is general. Size of queue is finite and the calling source is also infinite. Next is MMC GD infinity infinity model. This is a queuing model in which the arrival is Markovian and the departure distribution is also Markovian. Number of server is more than 1 and the service discipline is general. Size of the queue is infinite and the calling source is also infinite. So there are two more models left which you can take as homework, and at last let's discuss about some important notation and formulas of MM1 GD infinity infinity model. So in this picture you can see some notations and formulas of MM1 GD infinity infinity model: lambda, mu, probability of n customers in the system, probability of 0 customers in the system, and average number of customers and expected number of customer in the system and queue, expected waiting time per customer in the system and queue. So these are some important formulas.